Okay, good afternoon. So what we saw in the last class was I've clearly shown you the importance of, we started with by discussing about the importance of knowing about vacuum science. So to continue in that direction, if you look at okay, so if you look at this slide here, what it shows is a vacuum pump module. This is a pump modules. These are the pump modules, and you have the vacuum chamber there on the top. And this represents a simple thermal evaporation process, where you have a heater, you heat the charge, melt it, vaporize it, and then the vapor is deposited on a substrate. Okay. So the mean free path is the path that these pieces travel from the source to the substrate. That's called the mean free path. So the whole idea of thin film growth process is to maximize this mean free path. So it's a distance traveled. It's a distance traveled between the successive collisions is the mean free path. So if that can be maximized, if the distance traveled between successive collisions, so then we make sure that the evaporated species would reach the substrate, which is kept at a distance of anywhere from 5 to 10 centimeters in an unhindered fashion. So to that effect, if you look at the second point here, let's consider that each atom or molecule represents a target area of pi dc square, where dc is the collision diameter, right? So each atom presents a target area of pi dc square to other molecules. There are molecules all in random motion. Look, first is we may be doing a thin film deposition in good vacuum. There are no gas molecules. So the only gaseous species are those that are emanated from the evaporated charge. That's all. But then you may have to do sometimes a reactive way of thin film deposition. It means you start with a charge of titanium and you melt it. You create a plume of titanium atoms, and if these titanium atoms go on deposit on the substrate, you have a titanium thin film. But I can also make a compound by introducing nitrogen gas inside the chamber. So that means I get titanium to get nitridized, so I get titanium nitrate film on the substrate. So if it is only titanium deposition, I can do it in high vacuum, 10⁻⁻⁶ or -7 torr, so that there are no air molecules present inside the chamber to oxidize titanium. But then if I want to make a compound like titanium nitride, I need to have nitrogen gas inside. Or if I want to make titanium oxide, I can start with metallic titanium, and I have a partial pressure of oxygen inside, right? We talked about the partial pressures the other day, which means the emanated species also encounter the gas molecules that are present around them. Right? There's a reaction happening. There's also collisions happening between these gas molecules. So that's what I mean by saying that let each atom molecule represents a target area of pi dc squared to other molecules. So we talk about a binary collision each time the center of one molecule approaches within a distance dc of the other. Okay. Now let us imagine that the diameter of one of the molecules has increased to 2 dc. You increase the diameter by 2 times, while the other molecules are reduced to point charges. So while the diameter of one increases by 2 times, we are considering that the diameter of the other molecules become point charges. Then what happens in traveling a distance of the mean free path, lambda MFP stands for mean free path. So the former would sweep out a cylindrical volume equivalent to pi dc square times the mean free path. It's clear. Now the condition for one collision is that pi dc square lambda MFP times n is equal to 1. Then as an example, for air at room temperature and atmospheric pressure, this lambda mean free path, the mean free path for air at room temperature and atmospheric pressure, when the DC is considered to be, this is equivalent symbol. That box, what you see, it should have been is equivalent symbol. So when DC is approximate to 5 angstroms, then the mean free path for air at room temperature and atmospheric pressure turns out to be about 500 angstroms. That is 50 nanometers. Okay. So a molecule collides in a given time by, you know that, no? Lambda mean free path times by the volume. So under these conditions, air molecules undergo about 10 raised to 10 collisions per second. 10 to the power of 10 collisions per second. So this is why gases mix rather slowly, even though the individual molecules are moving at great speeds. And that is also the reason why we talk about the zigzag motion of gas molecules, right? So mixing of gases is not easy. Okay. Now since this N is proportional to the pressure, now the simple relation for ambient pressure and the mean free path is what is given there. So this lambda mean free path is equal to 5 into 10 raised to minus 3 by P. Okay. So this lambda mean free path is always in, if it is in centimeters, and P in torr. Okay. What you get is at pressures below 10 raised to minus 3 torr, that is a millitorr, your lambda mean free path is large. So I said the whole purpose of reducing pressure from a vacuum container is to increase the mean free path. So when at these pressures itself, you get sufficiently large mean free path values, which means that the molecules effectively collide with the walls of the vessel only. So whatever molecules that leaves from one point, if the mean free path is made large compared to the nearest component, right? So it's the lambda mean free path can be considered as so effectively the molecules then only collide with the walls of the containers. So that means there are no obstacles in between the place where the substrate is and from the point they emanate. There are no obstacles in between. These particles are free to go and reach the substrate. So this is simple depiction to show that if those are the atoms to be deposited on the other side, and if all these are the gas molecules, right? The purpose of the vacuum device, a vacuum pump, is, you need to first eliminate those gas molecules. In cases where gas molecules are not required inside the chamber, right? There are two ways in which thin film deposition can be done. I said, if it is a pure metal or an alloy that I want to deposit on the other side, then I need to create a vacuum where I don't want any gas molecules present. So these red balls, I would like these red balls to reach the other end, right, without having to collide with any of these gas molecules. You see, otherwise they always undergo these collisions, right? This is the problem always. So you can imagine if you remove those gas molecules by turning the pump on, right, you're sucking all those gas molecules. Then you have, that's a mean free path. So there's no hindrance for these atoms that are emanated from the evaporated source to reach that point. This is scenario number one, where there is no other gas present. That means you're doing the deposition in vacuum. But then if you are doing reactive kind of a thin film deposition, you also want these atoms to react with the gas, in which case you have a partial pressure of gas always present. So in that case, the moment the gas is present, the mean free path anyway comes down, right? So when the mean free path decreases, the deposition rate also decreases. So at high vacuum levels, you always have the best deposition rates. But if you're making a compound by doing a reaction on the other side, on the substrate side, with the presence of the gas, then the mean free path is affected, and the deposition rate also decreases. Okay, that's an ideal situation. You have a source, you heat it up, and you'd like all these molecules to go towards the substrate, and then get them themselves arranged in a perfect periodic fashion, and that's an ideal situation. That's a maximum mean free path you achieve. Okay. Well, in certain deposition processes, you'll see this, something like molecular beam epitaxy. The whole process is to maximize the mean free path, so that atoms that are generated from the source are clearly taken towards the substrate side without having to, without these atoms having to undergo any, additional collisions. Okay. Now there's what is called the gas impingement on surfaces, a very important parameter. So the gas impingement flux, okay, it's an important quantity that plays a role in vacuum science and vacuum vapor deposition, right? We're talking about the vapor deposition. It is a measure of the frequency with which the molecules impinge or collide with the surface, right? So I have a surface, I have these molecules continuously coming and impinging on a surface. That gives a parameter called the gas impingement flux. So as you increase the volume in a container, the container I showed you the other day, as you increase the volume in the container, right? That means by creating a vacuum inside, the gas impingement flux obviously decreases, right? So to start with, you have ambient pressure, you have more gas molecules impinging on the surface, and then you remove the pressure, increase the vacuum, the gas impingement flux decreases. So it is a measure of the frequency with which the molecules impinge or collide with the surface, and it's given by this simple relation: phi is equal to integral of Vx dnx. This is the number of molecules that strike an element of surface perpendicular to a coordinate direction per unit time and area. So, now again, going back to this equation, f of v, and from this, I want to tell you something here. In thin film growth process, in most of the processes where you give these relations, you don't have these relations coming from the first principle calculations. These are all derived as empirical laws and rules and equations from the experimental data, a large volume of experimental data, right? So we should take it that way. Okay. So combining all these, equations, what you get is the phi here, the gas impingement flux, works out to be something like n times root of RT by 2 pi m. Okay, that is a gas impingement flux. Okay. So wherever you don't have to derive this, you don't have to worry about remembering these equations, but most of these are empirical equations that in one way make us understand the processes involved during the growth process. Okay. Now again, going back to our equation for the mean velocity, root of 8 RT by pi m, and using the equation for pressure, nRT by N, this ratio, phi by Na, turns out to be P divided by root of 2 pi mRT moles per centimeter square second, right? And by substituting some of the known parameters, the phi works out to be 3.513 into 10 raised to 22 P by root of mt moles per centimeter square second. Okay. Now, what is okay? First, some equations, empirical equations, and some numbers, some constants there. So, what is the implication of the impingement flux? Then you'll understand better about what we are talking about. So, what is the application of the above development? Okay. So, you consider that a gas is escaping through a small orifice opening of area A. So, I have a container, I have a small opening through which the gas is escaping into a region where the gas concentration is 0, right? Something like that. So this is a container in which all those blue balls are gas molecules, and it's escaping through a small orifice, small opening of say cross-sectional area A, circular cross-section, right? Ideal approximation. Look, what we are trying to understand is this is a chamber, and then you have a small opening through which you want to remove all the gas molecules. That's what I'm trying to say there. Okay. Now the rate at which molecules leave is 5 times A, right? Gas impingement flux times the cross-section area. And this corresponds to a volume per second, V dot, right? dV by dt as 5 times A by N, so many centimeter cube per second. Now combining this with these two, the equation, combining this one with these two standard equations, what we get is this V dot, which is defined as the volume flow per second. Okay, that means you're looking at how the gas volume is decreasing as a function of time. That's all. So this works out to be V dot is equal to 3.64 times 10 raised to 3 root of T by M times A. Is that cross-sectional area, circular cross-sectional area, in units of centimeter cube per second. So for air at 298 Kelvin, that is at room temperature, this value corresponds to 11.7 times A, liters per second. That means in a given enclosure, if A is known, the cross-sectional area, that cross-sectional area times this constant 11.7 gives you some very interesting parameter in liters per second. Okay. What it is, what I'm talking about, you'll understand soon. But then this is always important. So for air at 298 Kelvin, the V dot corresponds to 11.7 liters per second. So in essence, what we have calculated is known as the so-called conductance of the circular aperture. See, just as we talk about conductance in electrical circuits, conductance also plays a very important role in vacuum components. After all, I need to create vacuum inside this, right? I'm connecting a pipe to it through a circular aperture. So through this circular aperture, I'm removing air molecules, right? Now, so you just remove the air molecules and convey it to the ambient. And this I do it either by connecting the vacuum pump directly to this body, which is not the case normally, right? We normally use tubes, and one end of the tube is connected here, the other end of the tube is connected to a pump. But ideally, right, if you calculate the conductance of a circular aperture there is a circular opening there. Circular aperture means you can imagine something like that. Yeah, that is a circular aperture. So if I know this cross-sectional area, for air at 298 K, your V dot corresponds to 11.7 times A, and so many liters per second of evacuation you're doing. So what we talk about here is the conductance of the circular aperture. And this conductance has a great deal of significance in pumping gases. So the importance of this, I'll tell you. Suppose you have a very good vacuum system. That means you design the chamber in a perfect way. You design the chamber in the perfect possible way, and then you also have the pumping modules. You'll know about those pumping modules, and you have very sophisticated pumps. But what you use to connect between the pump and these pumping modules, you don't take, if you're not taking care of the connecting tubes or ducts between a good chamber and good pumping module, effectively vacuum creation will not happen effectively in an effective way. That's what I'm trying to say. Okay. So this is one application. Now the second application is also very interesting. Now the question is, now if this is a chamber in which I want to deposit on a substrate, I do a simple thermal evaporation, and normally before the substrates of whatever size, 1 centimeter square, half a centimeter square, or 1 inch square substrates, these are mounted on the substrate holder. And I said substrate heating is also required. When you do that, you need to clean the surface before you put it inside the chamber, and then you start evacuating. So you take you want the deposition to happen on a piece of silicon, which is used as a substrate. So there is a cleaning process that is involved, because without substrate cleaning, you cannot expect to have, deposition on a pristine, pure surface. So substrate cleaning is always essential. But what you need to know is, even if you think you've cleaned the surface, how long it takes for a surface to be coated. Coated in the sense, it need not be a coating during the thin film growth process, even otherwise. That means, what it means is this coating, what I mean by this coating is contamination. So I have, see, if I have this surface, you think it's a clean surface, but you leave it outside, and if you make a macroscopic examination, it might look clean. But then you do a microscopic examination, you use a lens, and you see the dust molecules that are present there, right? There are all kinds of dust molecules, gas molecules can contaminate the surface. And the implication of this is also to show how long it takes for a surface to get coated or contaminated, so to say, by a single monolayer of gas molecules. That means so my thin film growth chamber is ready. I want to load the sample inside, right? And I clean the surface. I think I've cleaned the surface, but then you leave it on the table for about an hour. You take a break for lunch and go and come back thinking that, yes, I've cleaned the substrate. It is there in a small box, but still it's exposed to the ambient atmosphere. You know, it's not going to remain as a clean surface. What happens is, surprisingly, you know, see that? That's what what I'm trying to say here is, yeah, you see this, yeah. This is ideally, that's what I want. When during a thin film deposition, I want all these atoms to race towards the substrate and then deposit on the substrate. And what's the guarantee that your substrate is not contaminated? And this simple calculation tells you this issue is very important while depositing films in extremely clean environments. Extremely clean environments means, so vacuum above the level of 10⁻⁹ torr is called clean vacuum. It's not easy to achieve such vacuum levels, but basically vacuum of this order is called a clean vacuum. Now, surface analysis requires minimum surface contamination. So if I have a surface of a thin film or a single crystal, I want to do a very detailed surface analysis using a technique like ESCA or Auger spectroscopy or XPS, X-ray photoelectron spectroscopy. The surface should remain completely clean. The problem is, if you leave after thin film deposition, if you leave the substrate outside before you put it in the analysis chamber, surface analysis chamber, because some of these techniques are only, so to say, really surface analysis techniques. They only give information in a depth of just a few tens of angstroms. If the surface is contaminated by a few gas molecules, your analysis are completely going to be wrong, because you don't get a proper information from the surface, and this very sophisticated surface analysis tool that you use to analyze the surface, what you are actually doing is you're analyzing a contaminated surface. So the analysis time must be shorter than the time required for the impurities to accumulate, obviously. And there is what is called a characteristic contamination time. And this characteristic contamination time is the inverse of the impingement flux, right? It's very obvious, because there is an impingement flux. The inverse of it is I don't want anything impinging on the surface, which means I maintain the surface as clean as possible. And that kind of a scenario can be achieved only when the vacuum levels are less than 10⁻⁹ torr, or in terms of high vacuum greater than 10 raised to minus 9 torr, 10 raised to minus 10 torr, 10 raised to minus 11 torr. It's not easy to achieve these vacuum levels, but this is required to in order to do a very systematic surface analysis. 1 minute. Okay. All right. So yes. So we have the characteristic contamination time TC, which is the inverse of the impingement flux, and this can be calculated in this fashion. Again, starting with your this empirical equation for phi, for complete monolayer coverage of a surface, means for the surface to completely get a monolayer of coating, unwanted coating in this case, right, containing 10 raised to 15 atoms per centimeter square. So the above equation becomes this one, the TC I'm talking about, the impingement flux, the characteristic contamination time, which is the inverse of the impingement flux. This gives you, again, another empirical relation where your TC is, it comes from there, okay, you can easily go and get it, is equal to 2.85 times 10 raised to minus 8 by P in torr, pressure, times root of MT seconds. So many seconds, no? So using this relation, we should be able to calculate the characteristic contamination time of surface. Again, in air at atmospheric pressure and ambient temperature, assuming all the impinging atoms stick on to the surface, you know, we have the atoms coming close to the surface, and we assume that whatever is coming towards the surface, they also stick onto the surface. If that happens, in the ideal situation, that means the atoms come close to the surface and nothing is going away. This can also happen. So when these atoms come in, if the surface energy is too high, they can sort of re-evaporate the atoms back. So not all atoms that come in towards the substrate, they stick onto the substrate. Ideally, we would like to have all those atoms to stick on, but in reality, it doesn't happen because you're also providing thermal energy to the surface. Even a surface at room temperature has some thermal energy, 26 millielectron volts. So in air at atmospheric pressure and ambient temperature, assuming all these impinging atoms stick onto the surface, a surface will acquire a monolayer of gas, one single layer of a gas. You know, in what time scales? In about 3 to 4 nanoseconds. That's all. It's about 3.5 into 10 raised to minus 9 seconds. So 3.5 nanoseconds is sufficient for these one molar layer of gas molecules to settle down on a surface. This is amazing, right? Which means when I have when you have a substrate which you think you've cleaned it, before you put it in the vacuum chamber, the surface can get contaminated with the surrounding gas molecules in time scales of nanoseconds. Here it's 3.5 nanoseconds. So this is the reason why vacuum is required. So even if you plan to do a deposition, say after some time, you keep your substrates inside the chamber, and then you better evacuate the chamber and keep the whole thing in certain minimum vacuum level. What is that minimum vacuum level? Yes. Yeah. On the other hand, when you go to the extreme vacuum levels of 10 raised to minus 10 torr, which is not easy to achieve. See that the normal vacuum levels of 10 raised to minus 6 torr are achieved inside these working chambers within anywhere from 45 minutes to 2 hours. And sometimes you have to even you even pump the system down to almost a few hours. But from 10 raised to 6 to 10 to the power of minus 6 torr to 10 to the power of minus 7 torr to go to 10 to the power of minus 9 to 10 to the power of minus 10 torr, it takes a lot of effort. It takes a lot of effort. So in the ideal case where this chamber is, straight away evacuated to 10 raised to minus 10 torr, right? Idealistic situation, the best vacuum. So without the vacuum being present around the surface that is clean, the surface can get contaminated within 3.5 nanoseconds. But the vacuum, you provide a vacuum level of 10 raised to minus 10 torr, the surfaces can stay clean up to 7.3 hours. You see the difference. Nanosecond level contamination versus 7.3 hours of surface staying clean. That means at 10 raised to minus 10 torr, you don't even, this vacuum level doesn't even allow one monolayer of gas molecules to settle down on the surface, which is good. That's why high vacuum is always important. So surface exposure of gases is measured in unit called Langmuir, right? Capital L, and the units of Langmuir is pressure time units. These are torr second units, right? So that determines the surface exposure of gases at any given vacuum level. So you can extrapolate this. When there is no vacuum, the surface gets contaminated within a few nanoseconds. But at 10 raised to minus 10 torr, the surface contamination is minimal all the way up to 7 hours, right? So normally 10 raised to minus 10 torr cannot be achieved. So that means a surface can be saved from getting contaminated if you put it in a basic vacuum also, like of the order of 10 raised to minus 2 to 10 raised to minus 3 torr. Okay. So the conversion is one Langmuir is 10 raised to minus 6 torr seconds, which means that gas exposure could occur at 10 raised to minus 6 torr for 1 second, right? So nearly 3 Langmuirs, 3L correspond to 1 monolayer. Okay. So this example clearly demonstrates how important vacuum is, not only from the point of getting good quality thin films. Now you see, if I use the substrate which I think I have cleaned, but I have not bothered about keeping it in vacuum before the deposition is started, I am depositing these atoms on an already contaminated surface. That's it. That's why one has to use also clean rooms while handling substrates, so that you don't have dust particles floating around. We always have dust particles floating around, and these dust particles, since they settle down, when I leave this room and come the next day, I'll always see some dust particles sitting on the surface. And if I don't come into the room for 2-3 days, you'll see more number of dust particles settle down, which you do not see otherwise. Same thing happens to a surface. So it's for keeping the surface clean so that the thin film deposition is perfect in terms of getting only those atoms. I don't want any other set of atoms between the substrate and the atoms of the thin film. So if I have a different set of substrate, that means I have an impurity. For analytical experiments, again, you have used a very sophisticated experimental technique, and then you think you're done you want to transfer it to a surface analysis technique, but again made a mistake of not keeping it in vacuum before you transfer it to the surface analysis unit. You've already contaminated the surface. So the results you get are not, in addition to the results you get from the a thin layer of the film, you'll also get results from the surface contaminants. So important. Okay, I think I'll stop there, and we'll continue tomorrow. Okay, good.